Let me start. My name is Sun Nguyen. Um, I would like to present the co-work with my colleague from Ho Chi Minh City. Um, the paper is about feature selection and feature ranking based on intuitionistic fuzzy matrix and drop sets. So let me start with some motivation. Um, as you know, in drop set theory, redux are the main concept you can interpret this redux as a set of features or attributes that are most important. But this is not this is only the simple interpretation because obviously redux is the minimal set of attributes that maintain some good features of the whole set of all attributes. However, if you should remember that for given decision table, here you can see an example of decision table with 10 objects and 5 features or attributes. You can find many redux. This small table has 2 redux. So that's why you cannot say that you cannot evaluate the features on the base of one redux. You should look at all redux. So in rough sets theory, we are talking about the set of all redux, denoted, for example, here by red of the decision table. And if you look at the set of all attributes, all redux, you can also think about the degree of importance. So here, for example, in many rough set literature, you can see concept of core attributes. The core attributes are the set. The attribute is called the core if it occurs in each redux. Okay, so in every redux. So in this example, you can see that our decision table has 2 core attributes. It is A1 and A4 because you can see A1 and A4 occurs in both redux. You can talk about reductive attributes. That means that the attribute that occurs at least in at least one redux. So this is necessary because it's by occasion you have to use this. So attributes is usable. So for example, here you can see that A2 and A3, A1, A4, the first 4 attributes are reductive attributes because they occur in at least one redux. So, and this is interesting to see A5. In every time, all the redux, you've never seen A5. Obviously, I especially add this feature to show that this is in many decision tables there are some features that you will never occurs in redux. So you say that this is the redundant attributes. You can also extend this this idea. For example, you can define the importance of attributes by, for example, the frequency or the number of occurrences in redux. However, and you would like to have some ranking. For example, you have to rank the attributes according to this number of occurrences in redux. So you can say that, oh, this is the kind of a good ranking list. However, if you want to do that, you have to generate all the redux. So this problem is NP hard, and at this NP hard. So you are not able to do it for quite a high big data set. So now I would like to present our solutions very briefly because let's try it detail in the proceedings. Our solutions is based on the idea come from intuitionistic fuzzy sets, which is in fact it is quite close to this conference, because this idea has been proposed by Professor Anatasov, who had from Bulgaria, and he also had the invited talk at the first day of the conference. And the idea is to replace the typical fuzzy set, which is so by fuzzy set you should remember that the set is called fuzzy set if you can assign to each element of a given universe a value between 0 and 1, and you say that it's a membership function. So you can say that x1 belongs to some set A with some degree. So in intuitionistic fuzzy set, we assign to each element two values. This is membership and non-membership value. So you can say that, for example, x2 belongs to the set A, and for example, 50%, but do not belong to does not belong to a set A in 20%. So the difference between, so you can see that me plus ni should be should not exceed 1. However, the difference between 1 and me plus ni is called the intrinsic index or degree of uncertainty. And you can say a lot about this idea. And for example, this set of all pairs of real numbers between 0 and 1 with the sum not less or equal to 1 is a lattice, and you can also you can define in this way the additions and multiplication of operations for the objects. But now I would like to show another thing related to intuitionistic fuzzy set. This is intuitionistic fuzzy preference relation. So so this is the obviously you should remember that the preference relations is a relation in the typical set theory is the subset of the category the subset of the set of pairs. So so in case of fuzzy relations, in case of fuzzy relations, we can assign to each pair of objects a value, saying that how you can see that the different pair of objects belong to these relations. So the same to in the case of intuitionistic fuzzy relation, preference relation, because preference relation means that you prefer someone than some object than other objects. And so the so instead of single value, you will have two values as intuitionistic fuzzy sets. And this matrix where each element is a pair of me and ni, satisfying conditions that this is in the main diagonal you have 0, 5, and 0, 5, and you should have the conditions that me ij is the same as ni ji. So that means that, for example, here you can see that this is somehow in the symmetric positions we have the reverse value. And this kind of this IFPR is a very nice for modeling the problem of so-called ranking, because you can start to think about the ranking problem with in each position you have the kind of local comparison. You can compare two objects. For example, if you have 5 football teams, you can say that one team is better than other team in 51, for example, %, but the second team is better than the first team in 23%. In the overmatch, they draw. So, and if you have all of this information, so the question is, how can you rank all of these teams, 4 or 5 teams, so that it's somehow consistent with this matrix? And in this theory, you have 2 methods for to define the consistency. This is called additive consistency and multiplicative consistency. So by additive consistency, we mean that we are looking for the probability vector. So for each object, we assign one value W, kind of weight, but you assume that all the weights are non-negative and the total equal to 1. So that's why I told this probability vector. And in additive consistency, you assume that for each pair of I and J, Wi minus Wj plus 1 divided by 2 should be between mi ij and 1 minus mi ij. So this is a condition for additive consistent. And now some other model is called multiplicative consistent, means that you are looking for that the vector, the probability vector, so that the second condition is satisfied. Obviously, not every matrix. So for example, if you are giving some matrix, so the matrix is not necessary to be additive consistent or multiplicative consistent. That means this is not always true. This is not true that this probability vector always exists. So that's why you have kind of the optimization problem. You are looking for some additional value Lij and Rij. This means this is the kind of mistakes, and you would like to minimize the mistake. So that means that you would like to minimize these functions, and we can relax the conditions that we present here or here. So I don't want to go in detail with this model, but I would like to say that after solving this this optimization problem, we will receive the best ranking list. That means the best value of W, and this W denotes the ranking of the object. So we apply this idea to the feature ranking problem in that I mentioned at the beginning. So our idea is to present a method that start with decision table. We are using discernibility relations, and then we are constructing this intuitionistic fuzzy preference relations, and then we will apply either the model, additive model or multiplicative model to find the final feature ranking. Okay, so the idea is because of the time, I'm looking at the time, so I see that. So I would like to say that our method is we present few methods in our paper. The most simple, but the most basic method is based on discernibility matrix. That's it's done 40 years this year. And the idea is to share the information about, for example, if you say that if you want to discern a pair of objects, for example, here you have 3 and 1, you need to use either A1 or A5. So you say that A1 and A5 has, but now you can share the information and you show that, okay, so A1 and A5 are quite important for the pair 3 and 1, and each of them has the importance of each of them is, for example, 1/2. Why, for example, for the pair 7 and 6, you see only A1, so A1 is most important, and it is you have the way A1 here is 1. So you can change this discernibility matrix. You can enrich the information about this discernibility matrix by this function, as you can see here. So as I mentioned about sharing the information to 0.5 and 0.5, you divide this for the the occurrence of each features by the number of feature in each of these matrix. So here you can see that, for example, in 7 and 6, A1 is 100% necessary. But for 3, 1, A1 is only 0.5. So from here, you can define the me and ni value. That means how for each pair of object K and L, AK is better than AL by you define by this formula, and it's a detail. Here's an example. If you look at A1 and A2 only, so you look at these two columns, and you see that, okay, so A1 is better than A2 in for this pair. For example, 3, 1, 3, 2, you see that it's a bigger value. Here you see the same value, but here A2 is better than A1. So in this, you can define this set. That means the set X and Z and Y, and you can calculate, you can add the value, and then you calculate the value me and ni, saying that the attribute A1 is better than A2 in this degree, and A2 is better than A1 in this degree. Okay, so this is the main idea, and then you can we have the whole matrix, and you can solve, and you have the weights, and this weight will as a kind of feature ranking. And you can see that A5 in this ranking is the worst feature. A1 is the best one. In our paper, you can see all the formula and methods, because you can also compare both symbolic and numeric attributes. And you can also propose some method called the algorithm called RAFA. RAFA is the RAP fuzzy algorithm for attributes ranking. So and you have also the simplified version of RAFA, and all the methods is based on this diagram. And now, I would like to show some example applications, some experiment results. When if you are we are using our algorithm and you are comparing with other feature ranking, which is, for example, random forest feature importance is the state of the art for this method. That means this is one of the best method nowadays. So and you are comparing our RAFAR, SRAFAR, random forest, and no ranking. That means that you just use the given order of features. And for each of these ranking lists, for example, here you have 4 ranking lists. For each of them, we take only the first, for example, M features, and you create the subdata set and apply to some classifier, and you analyze the accuracy. You can see that, for example, in case of K and N, our method outperform both of our algorithms, RAFA and simplified RAFA. It's outperform the random forest feature ranking until, for example, here you see that until we have 19 features. The same in case of decision tree, our algorithm is at most, you can see that is in the same level as random forest feature ranking. But in case of SVM, again, our methods perform better than SVM. So that is, I'm going to conclude that we propose rough fuzzy hybridization technique to feature ranking, and our experiment in this paper we present only for a very not very big data set. Well, and you can see that you are happy because the accuracy seems to be quite good, and in the features you would like to attack to improve our methods for bigger data. I can say that our experiments also seem very promising, because for the data set with more than 10 million of objects, you can still perform with our algorithm, and it seems to be also very good. And this method has also many other nice features. For example, you can decompose the big data set into small pieces, and for each of them you can create, for example, this matrix, and then you can aggregate together. So this is all. Thank you very much for your attention.
Thank you, Son, for nice presentation. Now it's time for questions. The way to ask question is to write on the chat or just raise your virtual hand. Professor Skowron would like to ask a question, please.
I have rather a comment. Thank you very much for a nice talk. And my comment is related to your question, which you formulated after my lecture. And for example, here, you ask about this reasoning or judgment, and this can be related in this case to modeling of this membership function and non-membership function, which you are using here. Because if you define this function from the table, of course, you are you have these real numbers, but if you would like to say that these functions are really estimated on the real physical situations, for example, on the market and so on, you should have really a complex reasoning just going on from this situation to these numbers. Yes. So this is what is really a challenge also for this kind of problem. So this is my comment. Thank you very much.
Yes, thank you very much, Professor Skowron. I found that obviously at the beginning when Professor Anantaso proposed this idea, I found that there are many against and for argument for this, because someone say that, oh, this has been proposed also by Professor Zadek before, but obviously the semantic is quite interesting, because as you said, this two values, intuitionistic fuzzy values has quite nice interpretations. And in case of the experts, you can say that the membership and non-membership function can be somehow approximate. And again, you cannot say that it's 60% or 70%. Maybe you have to do it in some interval or some approximation.
Yes.
For direct value. But yes, I found that this could be this idea is quite close to Robs's theory also, but it can be used for many expert system where the judge can use this to.
Yes, and also another comment, if I can disturb, is also that when you have this interaction with the real world, you can also observe that this function may change over the time because of the changing situation in the environment. And so in this case is another problem to not only to derive just the static function, but to know how they are changing, and over this, how these models are changing. So, and how this reasoning can be performed just to, for example, to predict the changes of these models of the function and the whole theory. So this is what I would like to add. Thank you very much.
Thank you. Yes, I think that's is the diagram. I can also we can also model this. It's a changing concept or changing information by by modeling, because when you have data that is changing on time, so the information when you look at this the data can change, for example, from P1 to Pn, And the question is how to aggregate this information. You can forget about something. You can take only small parts of the past and you concentrate on the present information, for example.
Yes, this also is very nice interpretation here, because this dynamics of changing of the table not depends on us, but on an environment and changes in environment, of course. And without this link to the real environment, we cannot say anything, because of course, we can add something, we can change whatever randomly or not randomly, but this will be not related to the situation in the real world. Yes, so this is this necessity to have this link with the real world, with the physical object, as I was saying. So maybe you can consider this as a suggestion for future also, if you think that this is interesting.
Thank you.
Okay, thank you very much, Professor Skorron, for nice questions. And I can't see the other questions. Zainab Dagia, please.
Yeah, just Zainab. Yeah, I just have a question, please, concerning the number of features that you have used for the experiments, because you just said that you have tested it with the scalability in terms of number of instances, but in terms of number of features for the database already, how many features do you have in the data set that you have used?
For this paper, in this paper, the data set was not very huge.
13.
Yeah, it's a 30 attributes. And yeah.
And have you studied the scalability not only in terms of number of instances, because you have said that you tried it with large number of objects, more than 10 million or something that you said, but in terms of number of features, to how extent can you still have a feasible computation, let's say, and not that much expensive?
Yeah, because the main problem of this method is that we have to create this kind of matrix. This matrix is m times m, where m is the number of features. And we also we have some research related to the Partian, and this is only how to create this, how to make a decision or ranking list on the base of partial matrix only. So that means that you don't have to calculate the whole matrix, but for example, 50% of this. So this is also ongoing research in our group.
Okay, thank you very much.